So this is a numerical on bars in series subjected to temperature change. So let's see what is given first. Here the bar, steel bar of 40 mm diameter and copper bar of 30 mm diameter having lengths 1.2 meter and 0.8 meter, as well as their modulus of elasticity of steel and copper is given. Coefficient of thermal expansion of steel and copper is given, and they said if temperature is raised by 50 degrees Celsius, find stress in each bar. So we have given delta T is equal to 50 degrees Celsius. Now how to solve this numericals? We already discussed theory in earlier session, where we know that if bars are connected in series and fixed at both ends, then there is change in length due to temperature as well as due to this compressive force acting on this bar due to these supports. And we already derived equation for this. As delta L is equal to 0, we derived this equation, that is change in length due to thermal stress is equal to change in length due to compression force. So we will write this expression here also because concept is same. So to solve this problem, we know that change in temperature alpha L delta T of steel plus change in not change in temperature, change in length, that is alpha L delta T of copper is equal to, this is what, change in length due to change in temperature, okay, and is equal to change in length due to compressive force, that is nothing but PL upon AE of steel plus PL upon AE of copper. So we know that this is change in length due to change in temperature and this is change in length due to compressive force P. Now to solve this, we just put values here. Alpha values are given. So for steel it is 28 into 10 raised to minus 6 into L, length is 1.2 meter. So 1.2 into 10 raised to 3 into delta T is common, that is 50 degrees Celsius, into 50 plus alpha for copper is 18 into 10 raised to minus 6 into L is 0.8 meter, 0.8 into 10 raised to 3 into 50 is equal to this PL upon AE. So P, that is compressive force acting, that we have to find out. Let's say it is P. L is 1.2 into 10 raised to 3 for steel. Upon area we have to find out pi by 4 into d square. Diameter is 40 for steel into E, where E is 200 into 10 raised to 3. This is for steel, plus for copper it is again P into L is 0.8 into 10 raised to 3 as we are finding in mm upon pi by 4 into d square. Diameter is 30 square. E is for copper is 100 as given in GPA, we are putting in MPa because we want answer in mm. So by solving this, we can see here only P is unknown here. So by simplifying this, we get one equation, that is 1.44 is equal to, we can take this P term to one side, already taken. So it is P into 1.6092 into 10 raised to minus 5. So if we solve this, we get value of P on each member, that is on steel as well as copper. So P is equal to 89.485 into 10 raised to 3 Newton. This is value of P on each member. Now what we have to find out? Find stress in each member. Now to find stress, we know that, let's say I am writing here, as we know P, then stress in steel is equal to P upon area of steel, and stress in copper is equal to P upon area of copper. So it is very simple. P is 89.485 upon area pi by 4 into d square, that is 40 square. If we solve this, we get answer of stress in steel, and here P again same for copper, that is 89.48, of course into 10 raised to 3 because we are finding in Newton, upon area pi by 4 into d square, that is 30 square, is equal to answer. So if we solve this, we get answers as for steel and copper. For steel it is 71.2099 Newton per mm square, as we are putting P in Newton and area in mm square. And here for copper it is 126.593 Newton per mm square. So very simple. Just put in this formula, and how we derive this formula it's already discussed in previous session. You can refer that. So just by putting formulas we get value of P, and once we get P, that is compressive force on each member, we get stress in each member. So these are the values. Likewise we can also solve if some gap is given. If some gap is given, then just in this numerical we have to, means this term A, let's say this term is A and this term is B. So in that case we can write A minus B is equal to gap, and we can solve in the same way to get our answers. So we discuss now how to solve numericals when bars in series fixed between both ends, that is expansion is completely prevented, and if partially prevented, that if gap is given.